Folks, our lecture for chapter 6 comes in two parts. First part is via some handwritten notes that I'll take, and then the second part is based on some slides. Now, the slides don't do a great job of explaining why we're defining a particular thing a particular way. So I thought maybe maybe it's worth a little introduction to talk about the fact that actually it's a not unreasonable thing to do. We have talked about Newton's second law. Which, remember, the net force acting on a mass m is equal to that mass times the acceleration of the object. So we have a way to relate the acceleration, in other words, the change in the velocity of an object, to the net force that acts upon that object. Okay, so here lately, our deal with Newton's second law, and I'm going to write it two ways, once in words and once in symbols. In symbols, we get to remember that the force and the acceleration are vectors. They have direction associated with them. Mass is a scalar quantity. It does not have any direction. We've been using Newton's second law. If we can talk about all the forces that are acting, and we know the mass, then we can sort of solve for the acceleration. If you think of the net forces acting on a thing, they are the combination, they are the cause of a cause and effect relationship. And the acceleration looks like the effect. Here's everything that's doing, and they're going to produce some acceleration. It's not the only way to think about Newton's second law. I'd like to break apart the acceleration. And rewrite it so that it looks like net force equals mass times. Now, acceleration is the change in the velocity divided by the time. How much has the velocity changed? Divided by how much time did it take to do that? That was our definition a couple chapters ago for acceleration. So I'll keep up the symbology here. Sum of the forces equals mass change in velocity, change in time. Now, I'm going to stick to the symbology for a second because it lets us represent the idea that I'm about to explain in reliable mm, reliable algebra, algebra that we're familiar with. The change in the velocity is the velocity we have now. Um, at the end of time interval delta t minus the velocity we have at the beginning. Every time we have that triangle, we mean what we have at the end minus what we had at the beginning. There's no reason that we can't distribute the mass through the parentheses. And if I make the equivalent statement in words, it looks to me like this is a thing evaluated at the end minus a thing evaluated at the beginning. That thing isn't just the velocity anymore, it's the product of the mass and the velocity. As long as the mass isn't changing, then there's no problem here. But it looks to me like we're saying, all right, this idea, this product, mass velocity, what is it at the end of time interval delta t? And what was it at the beginning? Let's subtract them. That looks like that to me. It looks like the change in the mass velocity divided by the time. Mass velocity is kind of a mouthful. I'd like to give this idea its own name. I apologize for this, but the symbol, if we're going to write it in algebra, the symbol for momentum is a lowercase p. So we define a new thing, let's call it momentum. It is a vector because velocity is a vector. Multiplying by the mass doesn't change the fact that the right-hand side has some direction. So the left-hand side has to have the associated direction as well. If we make this definition, then we can go back. We could replace mass velocity with momentum. And here we could replace mv with vector p. So we end up rewriting Newton's second law. Oops. Net force is equal to change in momentum over time. And net force equals change in momentum over time. This is cool because it changes the causality a little bit. We're still representing forces as causes and acceleration or motion, changes in motion, as effects. But the way that I think about it and the way that I encourage you to think about it is a little bit different. We don't always know the whole story of everything that's acting. What we can measure, think to Galileo's experiment, right? That he's rolling the ball on the horizontal surface and reasoning that it won't, if we can ignore the forces that apparently act, it would roll forever, inertia, right? All we can measure directly in that case, like I'm not standing on that ball. I don't know how strong the air resistance is or friction or whatever, but I can, from here, watch that ball go and measure its mass velocity product. I can measure its momentum. I can measure that. I can record the changes in the motion over time. They must be as a result of a particular net force. So we're still talking about the effects and relating them to the cause. But we don't need to know the causes before we start. Newton's second law in this version, the F equals ma version, is predictive. Here are all the forces. What will the acceleration be? In this version, it's descriptive. The motion changed. The momentum changed. All right. Therefore, there must have been some net force that acted. All right. So this thing, momentum. Let's dig into some slides and see how it works.